Okay, so we are ready to start. This lecture is actually very short because it focuses only on hybrid algorithms. So I believe some people will be interested in this topic because they have been asking me a lot about combinatorial optimization. And also somebody asked me about combining a mathematical programming technique with a multi-objective evolutionary algorithm. So this is precisely the contents of this talk. And this afternoon, as far as I understand, Professor Figueira is going to talk about combinatorial optimization. He told me he gave some theoretical talks yesterday that you all enjoy, and you were talking about NSGA2 or something like that. And he was asking me, is that the only thing you use? I said, no, that's not the only thing I use. That's the only thing they will use, not me. And he was asking me about that yesterday. So, okay. Hybrid approaches, by definition, a hybrid is anything that combines two or more things. But in here, since I'm focusing only on multi-objective optimization, I will only talk about two specific types of hybrids. Those called multi-objective memetic algorithms, and I will explain what that is, and the so-called HyperHeuristics. In both cases, I am focused only on multi-objective, which is the reason why the lecture is not that long, because there is a lot of work on memetic algorithms and also a lot of work on HyperHeuristics for single objective optimization. But the focus here is only multi-objective. Okay. What is a memetic algorithm? The term memetic was coined based on the word that was introduced by this guy, Richard Dawkins, in a very famous book. I think it's from the 80s, called The Selfish Gene. This guy is a professor at Oxford University, but he's very well known for these books that he wrote in the 80s, in which he tries to explain to a very wide audience how natural selection works. Basically, he tries to explain evolution. And he gets into a big discussion trying to refute those people who believe in what we call creationism. Those people who question evolution and believe everything was created by God and should not be questioned. So it's an interesting book. And in this book, Dawkins defines this unity, meme, as an imitation unit, and he speculates about the possibility of having cultural transmission. This is a speculation because there is no scientific evidence that this actually happens. So, by extension, based on the root of the word, a memetic algorithm can be seen as an approach that attempts to imitate somehow cultural evolution instead of biological evolution, which is the typical evolution. The guy who coined this term was Pablo Moscato. He's an Argentinian who now lives in Australia. And basically, the definition given by Pablo Moscato to a memetic algorithm is the combination of any population-based approach with a local search engine. In our case, the population-based approach is going to be, of course, a meta-heuristic, and local search can be anything. Any mechanism we want can be used as a local search engine. So this is the pseudocode of a generic memetic multi-objective evolutionary algorithm. It's not very different from a traditional multi-objective evolutionary algorithm. The main difference is here in step number 8, because here we apply local search. The rest, if you see, is basically a generic multi-objective evolutionary algorithm in which I have a certain number of solutions, n individuals. I evaluate fitness or apply non-dominated sorting. And then I select and apply genetic operators. So the only difference is this step. There are, of course, a number of design issues related to memetic algorithms. For example, how often should we use the local search engine, which is applied based on a certain probability? This is a parameter we have to provide. for how long should we apply local search? On which solutions should we apply local search? Some people, for example, say, okay, let's try to improve the best solution we found. Others, they say, okay, let's take a random solution and let's try to improve it. Others try to improve the worst solution. So there are several possibilities. Of course, local search implies that you have a neighborhood structure. That's why memetic algorithms were originally designed for discrete search spaces. Because in a discrete search space, it's relatively easy to figure out how to have a neighborhood structure. If you are dealing with real numbers, it's difficult to imagine what a neighborhood structure will be. However, there are multi-objective memetic algorithms for continuous search space. This is an important question. How efficient should be the local search with respect to its effectiveness? And this is a difficult question, because when you perform local search, you are increasing the number of objective function evaluations that are being performed. So let's assume I have a multi-objective evolutionary algorithm that has no local search, and it performs 20,000 objective function evaluations. Then I add local search, I perform 10,000 evaluations more, but the result, the quality of the solution, the best solution found, improves only 0.01%. So the question is it really worth it to do 10,000 evaluations more if the improvement is almost zero? What sort of improvement would you expect when you apply local search? So it's a very important question when you design a memetic algorithm. How should recombination and mutation interact with local search? Should we apply local search to an individual that is already an offspring and has been mutated? Or should we do local search first and then apply the operators, recombination and mutation? Should we use Lamarckian or Baldwinian fitness assignment? In the early days of local search, people proposed two different schemes. These names, they come from the biological inspiration of these operators. Lamarck was a guy, actually, if you read Charles Darwin's book, The Survival of the Fittest, his book on natural selection or evolution, his theory of evolution, he cites a lot the work of Lamarck. Lamarck is considered by many to be the first evolutionist. He's the first guy who tried to prove that life evolved from very simple structures. However, his theory, he elaborated a theory, but his theory was wrong, which is the reason why Lamarck has been forgotten. He actually believed that a species could change during their time life. If certain species, for example, he said a giraffe, they have the neck, a very long neck, because for many generations, many years, the giraffe was sort of stretching out the neck to reach out for these leaves in high trees. So he was convinced that anything that happened to a species when it was alive, it will affect the offspring. For example, if you had a damage in your arm, or you simply cut off your left arm, somehow this will have an effect in your offspring. That was what Lamarck believed. This is, of course, not true, but the guy who proved this was proved in the 19th century. He did an experiment with rats. He cut off the tail of rats, recombined them for several generations, and he said, if Lamarck is correct, at some point, one of the offspring should be born without a tail. But that never happened. He tried like more than 2,000 rats. That never happened, and then he said, you see, this doesn't happen. Whatever happens to us physically has no effect in evolution. What has an effect is really the capability that we have as a species to survive. And this is the other theory, the Baldwinian theory. Baldwin was a biologist. He said that what will be affected somehow by evolution is intelligence. That intelligence, or the evolution of the brain, will be conditioned to survival. That means if we need to be smart to survive, we will be smart very quickly. If we don't need to be smart, then we will remain dumb. That's pretty much what he said. And he tried to give an explanation of the very accelerated evolution of the human brain. In terms of history of the world, the evolution of the human brain happened in a split second compared to the evolution of other species. We are one of the species that has been on Earth for perhaps the shortest period of time. And we are supposed to be highly evolved. But we are highly evolved only in terms of intelligence, but not in terms of adaptation. We are the species that has probably one of the lowest capabilities to adapt. If you look at insects, for example, insects have been on Earth for a very, very long time. Or some animals, some reptiles, like the crocodile. The crocodile hasn't evolved in about, 60 million years? They remain the same as in the time of the dinosaurs, except for the size. They are now smaller because they don't need to be big. They used to be huge. But that was because everybody else was huge. Even insects were huge. But so in terms of evolution, these species are much more evolved than us. But we evolved very quickly, apparently because of intelligence. Intelligence was evolved because nature decided, these species, they are too weak. They are defenseless. If they don't become smart, they are going to disappear. And that's pretty much the story of what happened. Now, we became too smart because now we are getting rid of the other species. But that's a different story. So in local search, when we say we use a Lamarckian scheme, that means that I am in a point, I have a solution, apply local search in the neighborhood of this solution, and if I find something better, this better solution replaces the original solution. In the Baldwinian scheme, you get a solution, apply local search. If you find a better solution in the neighborhood, then this affects the fitness of the original solution, but the original solution is not replaced. The most common is, of course, Lamarckian, because normally you want to replace by the better solution, but that doesn't happen all the time. Bill Hart, in '94, analyzed general aspects of these questions, but in a single objective context. Other people have suggested, for example, to use different neighborhood structures, some of which can dynamically change. You can have a neighborhood that is changing over time. But it should be clear that defining a good local search engine can be very challenging in some cases, for example, in continuous search spaces, and we will talk about that. So as a consequence, most of the early multi-objective memetic algorithms in the literature were really designed for discrete search spaces. Those problems that you are working on, job shop scheduling, traveling salesman problem, quadratic assignment, all these problems are discrete, so it's not very complicated to design a search engine for them. So we will see very quickly some of the early proposals of multi-objective memetic algorithms. We have, for example, the memetic version of the Pareto archive, proposed also by Joshua Knowles, the multi-objective genetic local search proposed by Ichibuchi. There was another a variation of this algorithm that was actually much better than Ichibuchi's algorithm, proposed by Jaskiewicz, and so on. Joshua Knowles presented in 2004, there was a book published on memetic algorithms, and he had a chapter in which he provided a review of multi-objective memetic algorithms. So quickly, some of these proposals, for example, Ichibuchi in '96, that's a long time ago, he proposed this simple multi-objective genetic local search algorithm, which uses a weighted aggregation function of the objectives to find out which is the best solution obtained from a local search procedure. This he uses for a scheduling problem. I don't remember exactly what sort of a scheduling, but it was a scheduling problem. In a further paper, he refines this stage of exploration by applying local search only to some solutions, not to all of them, only a subset of solutions. He decides to apply local search only to the fit offspring, which are those that are close to their parents in objective function space. Later on in 2003, he developed another variation in which he compared a local search engine based on a weighted aggregating function with the use of Pareto dominance. And his result was actually quite interesting. He found in his experiments that it was a lot better to use a weighted aggregating function than using Pareto dominance in the problems he adopted in his paper, which were knapsack and scheduling problems. So this went back in 2003 against the belief that linear aggregating functions were of no use. If you remember, I told you that was the closest thing to the devil for emo people. They didn't like linear aggregating functions. But he was able to show, with his experiments in this paper, was published in the IEEE Transactions on Evolutionary Computation, he was able to show that in some cases, like in these discrete problems, knapsack, this is binary knapsack, and some scheduling problems, it's not really true that linear aggregating functions are not a good choice. It's all the other way around. They are better than Pareto dominance. Yao Shujin, he developed the evolutionary dynamic weighted aggregation. We already talked about this. And he tried to compare the performance of using dynamic weights with respect to using another strategy in which instead of going random, the weights were systematically varied, which is the way we normally do it, right? We have a formula and we are producing combinations of weights. In a further paper, he tried to validate empirically that a property called connectivity was the key for the effectiveness of his approach in continuous multi-objective optimization problems. This is actually a very interesting idea. Connectivity is a property that he argues that is related to the topological structure of the true Pareto front. So when the property is present, all the solutions are connected both in decision variable space and in objective function space. And this, of course, facilitates the design of a local search engine because you can have a neighborhood structure. There are no holes in the neighborhood, areas of the search space that will lead you to bad solutions. Oh, there we go again. Yeah, it always does the same. Right? So this of course was a bit speculative because we don't really have evidence that this property actually exists. He just gave it a name when you have a nice neighborhood structure that makes easier to design a local search engine. His approach actually had a very good performance in most cases. He tested it with convex and concave Pareto fronts, and even with disconnected Pareto fronts in which obviously the connectivity property will not be present. But after that, nobody followed on this work. Joshua Knowles in 2000 proposed the memetic Pareto archive evolution strategy, which is a memetic variation of the algorithm we already saw. This one, if you remember, the original algorithm is based on a 1+1 evolution strategy. So it's a single individual that is mutated. This one has a population. Mu is the number of parents, lambda is the number of children, and then you take the union and you keep the best mu from that union. He also adopts crossover. The original algorithm has no crossover, only mutation. And he recombines the local non-dominant solutions, which is very interesting. He applies the operator to the local search, which is one of the points we saw in the issues when designing a memetic algorithm. So this algorithm uses two archives, one for keeping local non-dominant solutions and another one for the global non-dominant solutions. A local non-dominated solution is a solution that was non-dominated at one particular iteration, but later on became dominated by somebody else. Global means nobody dominates this solution now or from previous generations. So this guy has remained non-dominated for several generations. He also uses a population of candidate solutions, which are the departing points for the local search. So each of these candidate solutions is replaced by an improved solution obtained during the local search. So the search in this case is constrained to a certain number of movements because you cannot afford performing too many evaluations of the local search because that will be too costly. So he performs a fixed number of movements, generates an intermediate population, and that provides the outcome of the local search. And he tested this with binary knapsack problems. There is a further paper that is quite interesting actually from Joshua. It's not very well known because this paper was presented at some small conference in Australia. In this paper, he studied the details of what we call the fitness landscape of a multi-objective combinatorial optimization problem. It's the quadratic assignment, which is like the more general case of the traveling salesman. Traveling salesman can be seen as a special case of quadratic assignment. And in this paper, he analyzes different techniques and metrics to design a local search engine. So it's very interesting because normally people tend to design the local search out of their imagination. You know, anything that you want to do is valid. But in this case, he performs a more, we can call it theoretical analysis of the problem of the search space, of the neighborhood structure, and based on that analysis, he designs his local search engine. So it's very, very interesting. Other people, Hiroyuki Sato, for example, he proposed a different type of multi-objective memetic algorithm. In this case, the goal was to improve diversity rather than achieving convergence. This is also very unusual because normally what you want is to achieve convergence, not to improve diversity, but it's perfectly valid that the local search doesn't aim for convergence, that aims for diversity. Is of course possible, not very common. Kleeman, he proposed a local search that operates by levels and takes into consideration information of the domain, which is very common. Normally, most local search engines use specialized information to guide the search and focuses the neighborhood search into different regions depending on where he is. Jaskiewicz, he proposed these random directions multiple objective genetic local search. Is also another interesting algorithm, similar to Ichibuchi's algorithm. He again uses a weighted linear utility function. He can also use a Chebyshev utility function with random weights. But basically it's a linear aggregating function or a nonlinear aggregating function in which he combines all the objectives of a multi-objective problem into a scalar value. That's the way this works. This approach is based, of course, on the use of local search, but he also uses a sample of the best solution that were previously obtained by the algorithm. This is also very interesting because this is similar to a population in a genetic algorithm. And again, he applies recombination between individuals selected from this sample. This is similar to the idea of Joshua Knowles of applying recombination to the outcome of the local search. He uses quad trees to store non-dominant solutions. We saw that yesterday. Other approaches, for example, Caponi and Neri, they propose the cross-dominant multi-objective genetic algorithm, which is basically NSGA2 combined with two local search engines, a multi-objective version of Rosenbrock's algorithm, which is a mathematical priming technique, and Pareto domination multi-objective simulated annealing, in which, as you can imagine based on the name, he uses a multi-objective version of simulated annealing. Soliman proposed a memetic version of a coevolutionary multi-objective differential evolution approach. We will talk later today about differential evolution. Basile, he developed several hybrids of evolutionary search algorithms and multi-agent strategies. In this case, these agents perform the local search. Okay, all these examples I gave were for discrete search space. Now we will focus on continuous search spaces. Apparently, this paper by Kalya Moidev, this should be 2000 and 2001, I repeated the same year. They developed, this seems to be the first attempt to use local search in continuous search space. So they developed a weighted aggregating function for designing engineering shapes. And the approach, this local search engine is coupled to the NSGA2. So first, local search is applied only at the end of the search, when the algorithm has found a solution. But in a further version, the second one, local search is applied at each iteration to each individual. But this, of course, is too costly. Normally, local search is not applied like that. And as I say, this seems to be the first multi-objective memetic algorithm for continuous search space. Who proposed to use gradient-based local search, which is sequential quadratic programming, combined with NSGA2 and SPA to solve the ZDT benchmark suite. So in this case, what they show in the paper is that if there were no local Pareto fronts, then the hybrid approach had faster convergence. But the reason of the local Pareto fronts is that if you use a gradient method, obviously it's not going to work in that case, right? When you have a local false Pareto fronts or whatever you want to call them, or local Pareto fronts. So that's a limitation clearly of using gradients. Adra, he hybridized 3 local search techniques with a multi-objective genetic algorithm. He tried simulate annealing, a hill climber, and Tabu Search. Elizabeth Banner, she adopted local search based on quadratic approximations of the objective functions. And Rigoni and Poles, they hybridized an algorithm they developed, this MOGA2, with normal boundary intersection and nonlinear programming. Wang proposed an approach for constraint optimization that they call the hybrid constraint optimization evolutionary algorithm. And this combines niching genetic algorithm, which is based on tournament selection. And this best individual replacement scheme is used as local search. Scindia, he proposed and studied the combination of NSGA2 with a reference point method. This is actually, because this guy is an Indian guy, he did his PhD in Finland. This attempt was the first step towards the NSGA3. He did his PhD with Kaisa Miettinen and Kalja Moidev when Dev was in Finland. And this was the first attempt to extend NSGA2 by using reference points. So the main problem in multi-objective optimization, if you want to use local search, is how to define a neighborhood structure. This is, of course, a complicated thing to do. Basically, what people have done, and this is like the obvious approach, is to use the gradient. If you use the gradient of each objective, for example, this will be the gradient of objective 1. This will be the gradient of objective 2. Well, the problem here is, in single objective, the gradient gives you the best descent direction, right? But in multi-objective, you will have one direction for each objective. So the question remains, in which direction am I supposed to move? So what happens is, once you have the gradients of the objectives, you will generate this area that we call the descent cone. So notice it's not a single direction, it's a whole area, all this cone. It's an unsolved problem inside the cone, which should be the best direction that I could take. You could say, okay, why don't I take like the middle point, for example. Why don't I move in that direction? Okay, but the thing is we don't know which one is the best direction. The other problem, if you have used gradients, is not only to know the direction, but also how far are you going to move in that direction. This is something we normally call lambda. So when we try to use this in multi-objective optimization, we have to solve these two problems. To decide a direction inside the cone and to decide how far are we going to move in that particular direction. So this is our neighborhood structure. It's not completely straightforward, but it's not that complicated to do. It's possible. Several people have done this. So, for example, Bosman in 2005, he stated that finding an improvement direction for the multi-objective case is also a multi-objective problem. So finding inside that cone, which is the best direction, is somehow also multi-objective. So he claimed that the solution, this so-called multi-objective gradient, must be a set of movement directions in which some of the objective functions decrease simultaneously, while the others can either decrease or just maintain the same value. So this is Bosman. Bosman and Edwin de Jong, they proposed an analytical way to calculate these directions. He had some matrices, and you had to solve something in those matrices, and that's it. Once this set of descent directions is settled, then the thing is you will have several possible directions. So in his case, he randomly selected one of these directions, and he moved in that direction. This method was called Combined Objectives Repeated Line Search, CORL. And there was another improvement in 2006. In these two cases, this local search was applied using what we call an estimation distribution algorithm. This is a very strange sort of algorithm. It's considered an evolutionary algorithm, but strictly speaking, it's not. It's basically a probability distribution that tries to emulate the behavior of the evolutionary operators. So we generate a set of random solutions, same as in a genetic algorithm, but using probability theory, we try to produce the same effect that crossover and mutation will have on these solutions. But we never apply operators. All we apply are probability distributions. So he did that. He proposed this algorithm called Medea. So after applying the variation operators, they select a set of individuals that are moved using the gradient information, this core, and they obtain an improvement on fitness for each of them, and then the thing keeps iterating. What they found in the paper is that first, the local search had some problems. For example, in some cases, there was no improvement, and this is not supposed to happen. You always should have some improvement. Also, the results were inconclusive in the sense that the use of local search, of course, was not always helpful. In some cases, apparently, produced bad results or worse results than without using local search. Harada proposed the Pareto descent method for constrained multi-objective problem in cases where the solution lies in the boundary between the feasible and the feasible region, which is normally the case in multi-objective optimization. This algorithm has a polynomial complexity because the basic operations consist in solving systems of linear equations, and it's meant to be more general than core. They also use a randomized generator of solutions similar to a mutation operator from evolution strategies. And it worked, but the improvement was not that good. It was not that convincing. Like, okay, it works fine. We can buy the idea that you were able to reduce from solving nonlinear equations to solving linear equations is an improvement. But at the end of the day, we wanted to use local search to improve the quality of the solutions. And in this case, the improvement is marginal. It's not really that good. Brown and Smith were probably the first who analyzed this concept of the descent cone, which is conformed by the intersection of the negative half spaces that are generated by the gradients. They propose that the offspring of a multi-objective evolutionary algorithm must lie inside this cone. So that means you should perform recombination to generate children here in this area. However, in the paper, they never provide any sort of algorithm. That's why this paper is not highly cited. Bosman provided an algorithm, and Harada provided an algorithm, but not these guys. They also present a procedure to approximate the gradient of the objective functions using neighborhood information. But the problem is that if we use an improvement direction, as I mentioned, knowing lambda, which is how long this direction will be useful, is complicated. Normally, if you have used gradients in single objective optimization, you have to solve an equation to find out how far should you move. So in this case, if you try to do it analytically, it's not going to be one equation, but a set of nonlinear equations. So this is very complicated. So it may be harder to solve the equations to find the length of the movement than solving the multi-objective problem itself. So you don't want to do that. Other people, for example, Pradyumna Shukla is an Indian who got his PhD in Germany. He introduced the use of two stochastic gradient-based techniques to improve mutation in NSGA2. He used Schaeffler's stochastic method and Timmel's method. These two algorithms were competitive in some of the ZDT problems, outperforming the original NSGA2. But of course, ZDT4, which is multifrontal, has several false Pareto-Prons, could not be solved with the hybrids. And we did some work on this some years ago. Adriana Lara, who was my PhD student, co-advised with Oliver Schutze, we proposed the hill climber with side step. This is actually a very nice and intriguing idea. It was originally developed by a guy who was visiting us at Simvestab, a guy from Venezuela. This guy was from automatic control, not from computer science. And he came to visit me, and he said he wanted to take my course on multi-objective optimization. And in the course, they had to develop a project, so he chose for his project to do this idea, and turned out to be a very interesting idea. This is like the last version of the algorithm, because there was a previous version that was published, I believe, in 2007. This hill climber with side step is a local search strategy, which is very interesting because it can be used with gradient information or without gradient information. So unlike Bosman's approach that requires the gradient, in this case, the gradient is optional. Of course, if you use the gradient, then it's more powerful. You can converge faster. But if you don't use it, it still works. So the idea of this approach is to move towards and along the local Pareto set, depending on the distance towards this set. Later, with another PhD student I had, we proposed a hybridization with direct search methods. Direct search methods are those that do not require derivatives. They don't require the gradient. So we work with Nelder and Mead and the golden section algorithm. Saul, he did several hybrids, and they had a reasonably good performance. They were not as good as those based on gradients, but in general, we were able to reduce the total number of objective function evaluations performed. One thing I forgot to mention is when you use gradients, there is another issue, that if instead of giving to the user the exact gradient, you try to use finite differences, that is a bad idea. Because normally, when you apply local search, what you are trying to do is to minimize the total number of objective function evaluations that you perform. if you use finite differences, it doesn't matter what sort of finite differences you use, for each objective function evaluation, you are going to perform several evaluations, right? Because that's how the equation works. You will need 3, 4 evaluations for each objective. So this is not good because instead of decreasing the number of evaluations, you are increasing the number. So you need to use something else. In our case, we use something that is called automatic differentiation. There are some techniques in mathematics so that you can scale the number of objectives and the number of evaluations doesn't increase exponentially. It increases at a reasonable pace. So there are techniques for this, but this is just a word of advice if you want to do this. So with Saul, we propose a local search mechanism which is assisted by a meta model based on support vector machines. Support vector machines are some sort of neural network. And in this case, the local search adopts a free derivative mathematical programming technique. That means it doesn't require the derivatives. So first generates approximations of the Pareto optimal set using several aggregating functions. And in the second phase, we generate solutions departing from those solutions generated in the first phase. So applications of these algorithms, both in discrete and in continuous search spaces, these are, as I said, only multi-objective. So we have inventory control, this is discrete, operation strategies of the energy system of a building, parametric optimization of a Kalman filter, the bi-objective traveling salesperson problem, somebody was asking me about this one, airfoil shape optimization, and vehicle routing with time windows. In some of these topics, for example, vehicle routing, there are even surveys because many, many algorithms have been proposed. So there are papers that review the different techniques and the different variations because vehicle routing, you have it without time windows, with time windows, with several depots, and so on. There are many variations. Okay. If you want to know more about memetic algorithms, I provide here some reference. Well, multi-objective memetic algorithms. Some papers. This is the one I told you, recent advances in memetic algorithms. That's where Joshua had his survey. There is a whole book devoted to multi-objective memetic algorithms. And another kind of more recent review from 2012 that appeared in this handbook of memetic algorithms, published by Springer. Okay, now the second topic is hyperheuristics. Hyperheuristics are kind of a strange approach in which the idea is to combine different types of heuristics with the aim of combining their advantages so that the search engine can be more general. The need for hyperheuristics was born in some complex combinatorial optimization problems. There is a guy, I will show his picture, this guy, Edmund Burke. He's now a big guy in UK, he's a dean of some school. This guy, long time ago, back in the early 90s, he was working on some really complicated scheduling problems. And any meta-heuristic he used didn't work in all cases. In some cases, for example, genetic algorithm work. In other cases, Tabu Search work. In other cases, simulate annealing work. So he came up with the idea of what if I combine different meta-heuristics using a single control mechanism that decides when to use each of these meta-heuristics. And this is what he calls a hyper-heuristic, because hyper is above meta, something bigger than meta. So the idea is to have a more general search engine, and of course, in the early days, hyperheuristics were conceived only for single objective optimization and only for discrete search spaces. Because in continuous search spaces, we didn't even know how to use local search. So Some years ago, for example, Edmund Burke extended reinforcement learning with Tabu Search. This is sort of a heuristic selection method with a fixed size taboo list, and use this for multi-objective optimization. I will only review the multi-objective cases. There are few. And this, by the way, is the book in which he defines what a hyperheuristic is for the first time. So he has what he calls low-level heuristics that are selected based on certain scores or ranks, which are computed separately for each objective. And he reported that this framework was able to guide the search towards the promising areas of the Pareto front over a set of space allocation and timetabling problems. So he was dealing with these combinatorial problems. Timetabling is one type of a scheduling problem when you have a certain number of classrooms that you have to assign to students, for example, for classes or for exams. Rahik Kumar, he presented a genetic programming system that evolves heuristics for the biobjective knapsack problem. In hyperheuristics, one trend, and this is actually sort of a hot topic in this area, is to use genetic programming to design heuristics. Genetic programming is a genetic algorithm in which what you evolve is not a fixed string of binary numbers or real numbers. What you evolve is a computer program. And these computer programs can do anything you want. The problem with genetic programming is that it's normally computationally expensive to do these evolutions because you need very large population sizes. Back in 96, 97, John Cosa, who is the inventor of genetic programming, was, for example, designing circuits using population sizes of 16 million individuals. But of course, he had a high network of computers. He had like more than 1,000 processors, so he was running his populations in this huge network. So in this case, to pack a knapsack instance, an evolved heuristic iterates through the list of pieces still to be packed and is evaluated on each using profit and weight of the piece as its inputs. And when the evaluation returns a value of which is greater than or equal to 1, then it stops and the piece is packed. But these heuristics that he uses are all produced by an evolutionary algorithm, not by a human, which is something also very interesting. McClellan and Kidwell in 2011, they apply a heuristic selection method modeled as a Markov chain for the DTL set test problems. So this is one of the very few studies on the application of hyperheuristics for continuous multi-objective optimization problems. Most of the few applications available have been done for discrete problems. So this approach is based on reinforcement learning, and he keeps a set of weighted edges that represent probabilities of transitioning from one heuristic to another. So after each invocation, he updates these edge weights based on the performance of a heuristic. So the idea in this case, and this is the general idea in every hyperheuristic, is you have several heuristics stored, as many as you want. For example, H1 is probably differential evolution. Perhaps this one is a genetic algorithm. Perhaps this one is Tabu Search, and so on. And you have here your engine, and you start solving the problem applying one of these. The first choice may be random, so you say H2. You apply this for a certain number of iterations, and then you choose another one, for example, H1, and you start checking if by changing the heuristic, the results improve or degrade. Obviously, if they get worse, then this is not a good choice, so you try another one. So this selection scheme has to decide this. Normally, when designing a hyperheuristic, you try to select heuristics that somehow are complementary to each other. That means they don't behave exactly the same, right? One, for example, may be very good for discrete search spaces, which is the case of Tabu Search. Another one may be good for mixed problems, which is the GA. Another one may be good for continuous search spaces, which is the case of differential evolution. That's normally the idea. Of course, when you do it in a very specific problem, all the heuristics have to be designed for that problem. If it's job shop scheduling, for example, it has to be only for that problem. So you don't need to put a whole algorithm. What you can put is simply different local search engines, and that's enough. You don't need to put a whole meta-heuristic in there. So it's an intriguing idea. We have worked on this recently, and we have a multi-objective hyper-heuristic that works reasonably well in continuous search space. Another work is by Antunez in 2009. He described this multi-objective simple random simulated annealing hyper-heuristic that he used for a power compensation problem in electricity distribution networks. He had two objectives, cost and power loss, and he designed 6 low-level heuristics to move from one feasible solution to another. He uses basically simulated annealing for the search engine, and he decides which of these low-level heuristics to use based on the dominance between the new solution and the archive solution. So he uses a weighted sum, a linear aggregating function of the two objectives in the acceptance probability function. This is another interesting one, Brook. Brook in 2007 introduced amalgam. This approach manages a set of population-based multi-objective approaches, and he's producing new populations of solutions combining all these different approaches. The number of new solutions that he produces by each low-level approach is decided proportional to the percentage of the previously created individuals that remain in the working population. So in this case, the approach is a bit different. What he does is more similar to something that we call in evolutionary computation an ensemble. An ensemble is when you have, again, several heuristics, but in this case, for a given population of an evolutionary algorithm, all of them are going to be applied at the same time. For example, I have 10 heuristics, I have 100 individuals, so heuristic 1 is applied to the first 10 individuals, 2 to the other 10, and so on. But then they start competing, and whoever produces best results, that heuristic gains individuals, and you decrease the individuals of the heuristic that is having a bad performance. So at the end, you expect that a single one, or perhaps 2, will win. The others will disappear because they are not doing well in that problem. So that's amalgam. He calls this a hyperheuristic, can be considered as such, but strictly speaking, this is really an ensemble. It's very similar, but it's not exactly the same. So what remains to be done in this area? Well, for example, we are missing theoretical analysis of local search engines used for multi-objective memetic algorithms. Also, we need more research on continuous search spaces for multi-objective memetic algorithms and multi-objective hyperheuristics. The development of parallel multi-objective hyperheuristics, we have developed one very recently, but in general, is not an area that has been developed too much. An interesting idea will be to have indicator-based multi-objective hyperheuristics. We designed one very recently, but there are almost no papers on this. And of course, theoretical analysis of multi-objective hyperheuristics. So that's on this topic. I don't know if you have any questions at this point.
So in your strategy, combining NSG with the memory, the local approximation, are you using the scalarization function for local search, or
Normally people use that, yeah. We haven't used NSJ2. We have used other algorithms. But in general, most people use the scalarizing function because that's the easiest thing. Because if you use a scalarizing function, then it becomes a scalar problem. So doing the local sets is very easy, right? Because you just apply gradient or whatever you want in one dimension, rather than having, as I put it, cone, one gradient for each object. So it's like the trivial solution is to do that. It's of course not the correct way of doing it. It's just easy. Other questions? If you are dealing with multi-objective combinatorial optimization problems for your work, it's highly advisable to try to use local search. Because local search normally works very nicely. It tends to improve, well, if you design properly, the local search tends to improve a lot the quality of the solution without having to increase too much the number of objective function evaluations. Of course, it's not always possible. It depends on the problem. But if possible, this is highly advisable to use.
Is it advisable to use scalarization for combinatorial optimization problem?
For what?
Scalarization.
But what is the type?
Combinatorial optimization.
Combinatorial? Yeah, sure. It's possible. It's just, as I mentioned, some people found that in some discrete problems, using a linear aggregating function, for example, works better. That doesn't mean in all cases this will happen. For example, decomposition methods, which transform the problem into several single objectives, like Multiobjective, there is some evidence indicating that this algorithm is not that good in discrete problems. It works, but it's not as competitive as it is in continuous problems. And it's a similar idea, right? Very similar to add up all the objectives.
So when we are using scalarization, then there is no need of using extractor dominance. Because
normally no.
We have single objective.
Normally no. But in some cases it's used. In some cases, for example, MoIRD uses Pareto dominance for the external app. But strictly speaking, it's not necessary. Any other questions? If not, then we will move to the next lecture. This one is a long one, so I hope you bear with me, you don't fall asleep, or you don't have a heart attack or something. You see too many slides. But there's too many topics also I'm trying to cover here. Okay, I'm going to talk about all these algorithms and sort of the basics of each of them, and then the way in which they have been extended to multi-objective optimization. I won't stop too much into the details of each of them, the multi-objective extensions, only the general idea. And I'm providing several references in case you are interested. In fact, this book is very nice. It's a very old book from, I think, 2009. It's called New Ideas in Optimization. It's very difficult to find in Mexico because McGraw-Hill is kind of a weird publisher. They have an office in UK and an office in America, in the US. And somehow, being McGraw-Hill, both of them, they compete with each other. So if a book is published by McGraw-Hill UK, cannot be distributed in America, and vice versa, which is something really stupid. But that's the way they work. I don't know, they probably have changed this, but I had to buy the book from Amazon UK because it was not available in Amazon US or any other Amazon in America, only in Europe. So, and it's a very nice book because it provides introduction to several of these metaheuristics written by the guys who invented the metaheuristic, which is very nice. For example, land column optimization explained by Marco Dorigo. So it's a nice book. Okay, so we will start with simulated annealing. Simulated annealing It's a very interesting algorithm that was originally conceived based on a very old paper written by this guy, Nicholas Metropolis. Nicholas Metropolis was working at Los Alamos in the US in the early 50s, and in 1953 he wrote a technical report in which he developed a mathematical model of the evolution of a solid in a heat bath until reaching its thermal equilibrium. This was used for some application in Los Alamos. But nobody got interested in the thing, and they buried the report, forgot about the whole thing. Then in 1983, Scott Kirkpatrick, this guy, he was doing his a research visit or his sabbatical, something like that, in Los Alamos, and he found this report. And he realized that this mathematical model looked a lot like an optimization algorithm. So he proposed an algorithm based on the mathematical model developed by Metropolis. By that time, Metropolis was already dead. And he published this in Science. You know, Science and Nature are the very, very top journals in which every scientist dreams of publishing. Because normally journals in engineering, for example, the impact factor is what? 1, perhaps 2. If you publish in the Transactions on Evolution and Computation, it's 10, and that's about the highest it can get. But in medicine, journals have 15, 20 of impact factor. Science and Nature, they normally reach between 30 and 40, depending the year. So it's the highest, and this is the elite of science. It's extremely complicated to publish that. So he published in 1983 his paper on this algorithm that is entitled Optimization by Simulated Annealing. And the algorithm became very famous. Many people started to implement this and got excited about it. So the annealing process of a metal consists in raising first the temperature until reaching a certain point in which the atoms of the metal can move freely, which for us in the simulation will be, this means randomly. After that, the temperature is gradually decreased, forcing the atoms to rearrange in such a way that they can form a crystal. This is the process Metropolis was modeling. So during this process, the free energy of the system is minimized. And therefore, this cooling schedule, that is, how fast should I cool down the metal, becomes critical. This is very, very important. If we cool down the solid too quickly or too slowly, then the crystal won't be properly formed. Either gets a deformation of the crystal, or the crystal simply won't appear. So in terms of a search process, we can say that in these two cases, we will reach a local optimum rather than reaching a global optimum. That will be the analogy. So this is the algorithm. It's incredibly simple. It has really nothing on it. So you start with one solution. This is not a population-based algorithm. It's based on a single solution at a time. You start with this solution S0 with an initial temperature T0, and we need, of course, this cooling schedule. Over the years, people develop different cooling schedules, and there is one actually with which they prove convergence of this algorithm. Then we randomly select S, which is a solution in the neighborhood. This N represents the neighborhood structure. So this is meant for discrete search space. So select the solution, evaluate the objective in that solution, and we compare that with the initial solution. And we perform this subtraction. Delta, if delta is negative, that means that the value of the initial solution is greater than the value provided by the new solution. In that case, S0 becomes S. Otherwise, we randomly generate an X and check this. If X is less than this exponential, you see it's the same delta from here, and T is the temperature, then S0 becomes S. So basically what we are doing here, if we are minimizing, in this case, when moving to a point is, from where I am moving to another point is better, rather than always moving, what I will do is to use a probability to decide when to move. So it's a very simple change with respect to a hill climber. In a hill climber, whenever you have a good point, or a point that is better than the current point in the neighborhood, you always move to that point, always. Or at some point, of course, you will get stuck, because if you are in a flat region, then all the neighborhood will have the same values. So this sort of avoids that the algorithm gets trapped in a flat region. However, this can still happen because it's operating with a single solution at a time. It's not particularly powerful. So simulated annealing generates local movements in the neighborhood of the current state and accepts a new state based on a function depending on this current temperature. The two main parameters are the number of iterations and the cooling schedule. The cooling schedule is the critical one, of course. So despite the fact that it was originally intended for combinatorial optimization, there have been proposals of simulated annealing for continuous search space. The key to extending simulated annealing to multiple objectives lies in determining how to compute the probability of accepting an individual introducing Pareto dominance, because in here it's only based on a direct comparison, right? We compare directly objective function values. So if we had a multi-objective problem, we will have to compare in terms of Pareto dominance rather than the value of the objective. Paolo Serafini in 1994 proposed the first version of multi-objective simulated annealing. It was a very interesting paper, pioneering work. He uses goals and adopts this algorithm to solve biobjective problems. So in this case, an individual is accepted with a probability P. He uses an archive of non-dominant solutions, which is also very interesting. But he only uses local dominance to filter out or to trim or prune the contents of the archive. And he experimented with different functions for the probability. For example, this is one of the functions he used. In this case, P, this capital P, is the probability of accepting X prime given X and a temperature T. And these weights, lambda j, are initialized to 1, and he modifies them during the process. He uses other probability functions, for example, con-ordering, which is similar to lexicographic order. And he has many things in this paper from 1994, including a sketch of a theoretical analysis of convergence of his approach, which is also quite interesting. Ulungu, he proposed a similar approach to that of Serafini, called MOSA, multi-objective simulated annealing. In this case, the probability function is this. You can see it's very similar to Serafini's. K is the number of objectives, and the weights are defined based on goals. Saisak and Jaskiewicz, they propose Pareto simulated annealing. This is also very interesting. He uses an aggregating function, but this algorithm uses a population. This is kind of unusual because simulated annealing is not meant to be a population-based meta-heuristic. They also use a secondary population and quadtrees for storing non-dominated vectors. Ray, he adopted simulated annealing with a linear aggregating function in which the weights are computed following guidelines from multi-attribute utility theory. He also uses a membership function. This is from fuzzy logic to handle the incommensurable units. If you remember, incommensurable means they are given in different units. And then after doing the transformation of the multi-objective problem to a single objective one, it turns out this problem is highly multimodal. So he he proposes a hybridization with nonlinear local search to solve this problem. So he, at the end, after trying several algorithms, he uses Hooke-Gibbs with an external penalty function. If you have taken some optimization course, you know Hooke-Gibbs is a direct search method, doesn't require derivatives. So Ruiz-Torres, he used simulated annealing with Pareto dominance for solving a bi-objective parallel machine scheduling problem. This is also an interesting paper because he compares several approaches. And for simulated annealing in particular, he tried two types of search, one that minimizes the number of delayed jobs, and another one that minimizes the time of the average flow. And furthermore, he uses a local search engine to explore the neighborhood of the good solutions. Hansen proposed another interesting approach using a normalized aggregating function for a problem in education. It's a very interesting problem in education. It's an optimization problem. I have no idea what problem that is. And the problem that results from using this normalized aggregating function is a single objective one. So he applies conventional simulated annealing with something that we call geometric Cooling schedule. This is the schedule that is normally suggested for simulated annealing when you have no idea of the problem that you are solving. This, we can say, the default function for varying temperature. So something interesting is they use fitness sharing, which is a technique normally used in evolutionary algorithms, but he uses this for diversity. Other approaches, Chang, he used simulated annealing with an aggregating function for optimizing financial portfolios. In this case, there are constraints that need to be satisfied in an exact manner, which is the value of the expected return. So he uses an additional heuristic just to handle this constraint. Lusig and Teodorovic, they use an aggregating function in an aircrew rostering problem using a threshold to determine the thermal equilibrium. And the threshold is computed with another aggregating function in which the intention is to check what improvement was achieved in each objective after a certain number of iterations. And the algorithm stops when there is no improvement anymore. Many other approaches exist. I'm not going to get into the details of all of them. This is an interesting one. This was developed at Cambridge University by this guy, Geoffrey Parks. They use, in this case, Pareto dominance, secondary population. But this problem they are solving is the design, the optimization of a bicycle frame. And they develop a continuous version of simulated annealing for this problem, because it's a continuous optimization problem. Balram Suman, he proposed another multi-objective version of simulated annealing based on Pareto dominance. He uses an external archive and a constraint handling mechanism to determine the probability of moving to a certain state. So it's another interesting paper. Suman, he did several other versions, and he has some interesting comparative studies. For example, in this one, he compares several versions of multi-objective simulated annealing. S-MOSA, U-MOSA, PSA, W-MOSA, PD-MOSA. All these, the last two are proposed by Suman. PD-MOSA is basically SPA, but instead of using an evolutionary algorithm, he uses simulated annealing. He uses also a penalty function to handle constraints. And he concludes, this is very interesting, that PSA produces the best results in terms of quality. PSA was developed by Sysak. It's not the algorithm he developed. So he's very honest, saying, you know, I didn't win. But PD-MOSA provides the best results in terms of diversity. Then Professor Sangamitra Bandyopadhyay in 2008, she proposed the archive multi-objective simulated annealing. This is really a hybrid between an evolutionary algorithm and simulated annealing. But this is perhaps the most powerful multi-objective optimizer based on simulated annealing that we have available. The code, the source code of AMOSA is available in the public domain. You can download it. And they use this concept of amount of dominance, which is measured in terms of hypervolume. And they use this to determine the acceptance of a solution. And also they use an external archive to store the non-dominant solutions generated by the algorithm. They compare with respect to NSGA2 and the Pareto archive using several performance measures. And something very interesting is that AMOSA can be used for many objective optimizations. So they use it for problems with 4, 5, 10, and even 15 objectives. Kalya Moidev is also co-author of this paper, if I remember well. There have been also hybrids with other meta-heuristics. For example, this guy, Robert Dick, he proposed a very strange approach in which he uses clusters of solutions and assigns ranks, but not to each solution, to the whole cluster, which is also very, very strange, very unusual. And he applies also operators to the clusters, not to the individuals in the clusters, to the clusters themselves. So he combines one portion of a cluster with another portion of another cluster. And he considers hard and soft constraints. So any individual violating a hard constraint is eliminated, and whoever violates a soft constraint is penalized. He uses Boltzmann selection. That's another name for this expression, this exponential formula of simulated annealing. It's called also Boltzmann selection. And combines concepts from a multi-objective genetic algorithm with a selection technique that was proposed by Goldberg called parallel recombinative simulated annealing. So applications, there are many applications of multi-objective simulated annealing, as you can see. Some in networking, network topological optimization for packet routing, flow shop scheduling, design of controllers, facility layout, inventory planning, electrical discharge machining, and so on. So it has been used a lot. It's an interesting algorithm. If you want to know more, there is a survey, which is not very recent, from 2006, and also in my book you can find more about multi-objective simulated annealing. The next approach is Tabu Search. Tabu Search was proposed by this guy, Fred Glover, in the mid-1980s. And it's also kind of an intriguing idea. The only book available, as far as I know, on Tabu Search is the book written by Fred and Manuel. Manuel is a Mexican guy who migrated to the US. He's now already a US citizen. He works at the University of Boulder in Colorado with Fred Glover. And this is the main reference on Tabu Search. So this algorithm has 3 components. A short-term memory that is meant to avoid cycling, that the algorithm cycles itself. An intermediate-term memory to intensify the search. This will be like a crossover in an evolutionary algorithm. And a long-term memory to diversify the search. This will be mutation in an evolutionary algorithm. However, something interesting about Tabu Search is not probabilistic. This is a deterministic algorithm. It is possible, and some people have proposed probabilistic versions of Tabu Search, but the original algorithm is deterministic. That means each time you execute the algorithm, you are expected to obtain the exact same result if you provide the same inputs. Unlike evolutionary algorithms, they produce different outcomes. So I'm not going to go into the details. It's very similar to simulated annealing. The main difference here, because it also uses a neighborhood structure, it also moves to the next state in the neighborhood and so on. The main difference is this list called T. T is called the taboo movements, and that's the reason for the name of the algorithm. Taboo means forbidden. So what they do is all the recent movements performed by the algorithm go to this list. And for some iterations, the algorithm is not allowed to revisit these states. because it was already in those states. After some time, you can delete the Tabu search partially or totally, and then you can revisit those states that were visited before, but not in the short term. So that's really the only difference with respect to simulated annealing. So Tabu search can be seen as an algorithm. It's a hill climber because it's not probabilistic. All the movements are deterministic. It's a hill climber with memory. But this memory makes a big difference. Memory is important. So this is the explanation. And this is what I just mentioned, that the Tabu list makes Tabu search to be different from a simple hill climber. So at each step of the algorithm, a best movement, which is defined in terms of the evaluation function, this best movement is chosen. And in this case, the movements that it performs are more aggressive than when using simulated annealing. So this algorithm tends to generate moves that are in the area surrounding a candidate solution. So the main problem for extending this to multi-objective is how to maintain diversity. And also how to use the Tabu list. Can we exploit somehow this Tabu list? Those are the main issues. This is an interesting story. The two first proposals of multi-objective Tabu search were given the exact same name, because if you are the first in extending a meta-heuristic to multi-objective optimization, probably the acronym you are going to come up with is the most obvious, right? In this case, MOTS means multi-objective Tabu search. It's kind of the obvious acronym. However, you will see that this is called MOTS star. You will see next why it's called MOTS star. So Hansen proposed this approach in '97. And this is an algorithm that starts with a randomly generated population, applies a vector of weights, and the weights are varied throughout the search process to generate all the Pareto from, also uses an external archive. So it's a relatively simple algorithm. The reason why they had to use the star is because at about the same time as Hansen, this guy, Xavier Gandiblo, is a friend of mine, he submitted another paper in which he also proposed a multi-objective extension of Tabu search, which was also called MOTS. It turns out that the same reviewer evaluated the two papers. And he said, you know, we cannot have the same name for the two algorithms. So strictly speaking, this was submitted before the other. So this got the name MOTS, and the other one had to be MOTS star, because it was second, not first. So this approach is based on the use of an utopical reference point. This is similar to the displaced ideal from Milan-Seleni, and use also an aggregating function to minimize differences with respect to this utopical point. And it uses, this is interesting, it uses two Tabu lists. One contains the weights, and the other one prevents the algorithm from revisiting points that had been previously visited. Hertz, in '94, he proposed 3 ways of extending Tabu search to solve multi-objective problems, using a linear aggregating function, lexicographic ordering, and the epsilon constraint method. And basically, the one that sort of worked was the third one. I remember when I was a PhD student back in '95, I sent Goldberg an email asking him if he was aware of any papers on multi-objective Tabu search. And he told me he only knew one, which was this paper that he sent, which is a very interesting paper, and few people knew at that time about that paper. Other proposals, these Japanese guys, Kurahashi and Terano, they propose a hybrid between a genetic algorithm and Tabu search. Again, they use 2 Tabu lists in which the best individuals generated by a genetic algorithm are stored. So the best individual produced at each generation is stored in one list, and the best global individuals are stored in a second list. This was presented at Gecko back in the year 2000, long time ago. Hansen, again, is the same Hansen. he proposed another Tabu Search for combinatorial optimization, Tamoko, which is a variation of the algorithm he proposed before, from MOTS star. In this case, he uses a mechanism that forces solutions to move along the Pareto front, which is a very interesting idea. And also he discusses other schemes to deal with situations in which most of the solutions are non-dominated, and proposes to use a degree of dominance, which is very interesting because in 2000, people in multi-objective evolutionary algorithms were not aware yet of the difficulties of dealing with many objectives, with 4 or more objectives. And this situation was something that nobody really considered. It was until 2004 when Farina, Marco Farina, an Italian guy, he came up with the idea of relaxing Pareto dominance. However, before him, other people in operations research, like this guy Hansen, had already proposed to relax the Pareto dominance relation. So it's very, very interesting. He also uses quad trees and uses a weighted Chebyshev metric for the aggregating function. So Tamoko was compared to Pareto simulated annealing. And again, nobody seemed to be able to defeat PSA. This guy, he reported that PSA produced better solutions with respect to a metric that he defined, but he was able to show that PSA was unable to generate the whole Pareto front, and Tamoko could generate the whole Pareto front. So he convinced the reviewers and managed to publish his paper. It's like the other guy is better, but I covered the whole front, and the other algorithm is not able to do it. He also discusses in other paper from the year 2000 other aggregating functions based on the LP normal instead of the Chebyshev function. And in this paper, he uses a multi-objective version of the traveling salesman problem. And you can see it's a very old paper from the year 2000, published in the Journal of Heuristics. Some years ago, for reasons that are unknown to me, some friend of mine who is an operations research guy, he asked me, is it true that the Journal of Heuristics doesn't publish papers on evolutionary algorithms? And I say, why? Why would that be the case? But apparently, for some years, the journal had that reputation. But that is no longer true. Actually, I am an associate editor of the Journal of Heuristics, and I can assure you that they publish papers on evolutionary algorithms. Okay, by Kasoglu, he proposed an approach called MOTS, which adopts also 2 lists. The first is called Pareto list and stores non-dominant solutions. And the second is the list of candidates that stores all the solutions which are not globally non-dominated, but were at some point locally non-dominant. So this is very interesting because these local non-dominant solutions can be used to diversify the search. So it's actually a very interesting idea to do this. So these solutions are used as seeds to diversify the search. So they use compromise programming, and this is validated using several engineering problems. They compare with respect to NSGA, the original NSGA, and Moses. Moses was a system I developed in my PhD thesis, and I thought nobody would ever read that, but a few people did. Ho, he extended Tabu Search for multi-objective optimization with several approaches. For example, uses Pareto ranking, an external archive which is bounded, fitness sharing, a local search engine based on this strange idea of the hypercrowns. And they also use the contact theorem from Sixka to determine if a solution is Pareto optimal. So it's a very bizarre approach. They combine many things. It has 2 possible termination criteria. The first is a maximum number of iterations given by the user. But the second is when the external archive is full and the density of points of each of its members exceeds a certain threshold. Very unusual thing. But you can see it was published in the Transactions on Magnetics. And I believe actually that these guys, this society, they have a conference each year, which is like the top conference in the area. And my understanding is that papers accepted for the conference, they are published in the journal. But these are short papers, as you can see. only 3 pages. So Jaegi, these are again the people from Cambridge. They propose a parallel multi-objective Tabu search procedure for continuous search spaces. This is also very interesting. This is called also MODS, and this approach combines hook heaps with 3 memories. So rather than using a hill climber, they use a mathematical programming technique, a direct search method, but use Pareto dominance and generalize the movements of hook heaps for the multi-objective case. So this version of hook heaps allows uphill and downhill movements, and it's, they claim it works better. This was presented at PPSN in 2004. They use a pattern search strategy. Pattern search is the other name that some people give to hook heaps. And this is used to speed up the search along the descent direction. The medium-term list is replaced by an external archive that stores non-dominant solutions. So you can see most of these multi-objective extensions use an external archive. And the intensification process is based on the use of points that were discarded by the hook heaps method during the search, and use a functional decomposition that allows the parallel execution of the objective function evaluations at 2 stages of the search process. One is when performing the movements from hook heaps, and the other one is during diversification. This is actually very interesting because what they do is they use several threads, and in each thread they are running a Tabu search algorithm, and then within that thread they trigger a local search. So it's a very interesting implementation. They compare this with NSGA2 using some standard test problems, and they show that in general the algorithm is competitive. They only lose in one problem. And then they solve an aerodynamic design problem. But interesting enough, in this case, they present no comparisons. Well, you know, we are almost as good as NSGA2. Then we're going to solve this problem. Can the NSGA2 solve the problem? I don't know. I just wanted to try my own algorithm. And then they add a constraint handling mechanism, which is very simple. A solution that violates a constraint is considered as taboo, and we cannot revisit this point. So this is an interesting approach. So another, there are other extensions, of course. For example, Cultural Konak, he proposed this multinomial Tabu search. This is one of those versions that are probabilistic. This is not a deterministic version. It uses a multinomial probability mass function to select an objective at each iteration. And then in the external archive, they use Pareto dominance. So for selecting, they select based only on one objective. But for the external archive, they use Pareto dominance. Xu, he uses an aggregating function with a set of rules based on Pareto dominance for evaluating the neighborhood moves. And all these were published in top journals. This is the European Journal of Operational Research. So applications, there are quite a few. Groundwater remediation, turbo machinery, flow shop, row layout, distribution system planning, flying structure scheduling, power distribution systems, resource allocation, scheduling routing, and so on. So it has been also a relatively popular algorithm. So do you have any questions so far? We already covered 2, simulate annealing and Tabu search. And if you don't have any questions, then we will have a break, and we'll come back in about 20 minutes.